Welcome to the deep dive. Today our mission is to look at, well, really the future of high-performance metals. We're doing a deep dive on hybrid composites and specifically how to take something like aluminum 7075.
Which is already a workhorse alloy, a real backbone material.
Absolutely, a crucial alloy, and make it nearly 40% stronger.
Yeah, you see AL7075 everywhere in high-stress components, aerospace, high-end automotive. Its strength-to-weight ratio is already fantastic. So the challenge is, how do you push that envelope further?
Without breaking the bank on production methods.
Exactly, without introducing wildly expensive new processes.
Okay, so let's get into this study. They're reinforcing the standard AL7075 matrix with not one, but three different things. We've got fixed amounts of graphite, that's GR, and zirconia, ZrO2. And then they vary the main event, which is boron-carbide, or B4C.
And the whole point there is what we call synergistic strengthening.
Yeah.
They're blending these hard ceramics.
The zirconia and the boron-carbide.
All right, those bear the load. And then you have the graphite, which is a solid lubricant to minimize friction. And importantly, they made this material using the two-step stir casting method.
Which is very economical, right? That's key.
Crucial. Stir casting is one of the cheapest ways to mass produce these composites commercially.
So after all the testing, where did they land? What was the optimal sweet spot for these reinforcements?
It was pretty clear. The best overall performance, both in strength and wear resistance, was consistently found at the maximum B4C content they tested.
And that was?
4 weight percent.
4%. Okay, so let's start at the foundation. The microstructural integrity. The SEM imaging confirmed these particles weren't just, floating around in there.
No, not at all. You get a really uniform dispersion. The GR, the ZrO2, and the B4C were all strongly bonded within the aluminum matrix, and that's essential.
You have to have that foundation.
And you see that integrity reflected immediately in the mechanical numbers. So the base alloy starts at 68 Brinell hardness.
Okay, 68 BHN.
And this optimal 4% blend, it peaked at 87 BHN.
Wow, 87. That's a 28% enhancement.
It is. You're looking at a material that's over a quarter more resistant to permanent deformation, all thanks to those hard ceramic particles acting as internal barriers.
And those strength gains, they translate directly to real-world application. They saw this enormous leap in ultimate tensile strength.
A 37% jump.
Yeah, from 214 MPI all the way up to 293. And yield strength saw an even bigger gain, 40%.
I mean, you've essentially given an already tough component nearly 40% more load-bearing capacity.
But there's always a trade-off, isn't there?
There is, and we have to address it. While it got dramatically stronger, the toughness did take a hit. Ductility decreased.
How much of a decrease are we talking?
Elongation dropped by about 14%. So from 14.2% down to 12.2%.
Wait, a 14% drop? That sounds pretty notable. Does that compromise its safety factor in something like a crash structure where you need impact absorption?
That is the critical question. And it confirms the fracture mode shifted from a classic sort of stretchy ductile failure to what's called a quasi-brittle failure. It just means engineers have to account for a slightly shorter yield to failure window.
I see.
But for static parts or high compression environments, the huge increase in load capacity far outweighs that small reduction in flexibility.
Okay, so we've accepted a slight loss in flexibility for a massive gain in strength. But what about long-term durability? How did it hold up under constant friction?
The wear results were phenomenal. They used standard pin-on-disc testing. At the highest applied load, 40 newtons, the 4% B4C composite showed a 34.8% decrease in wear loss compared to the base alloy.
That's incredible. Over a third less wear? What was happening on the surface to cause that?
The surface analysis really showed that synergistic effect in action. I mean, the base alloy just got torn apart. Severe adhesive wear, deep grooves.
But the composite
are much smoother worn surface. Minimal grooving. It's like it has this internal self-protection system. The B4C and the ZrO2 act like armor plating, resisting penetration.
And the graphite is the lubricant.
Exactly. The graphite is in there acting as this continuous solid lubricant, minimizing friction and stopping material from getting ripped away.
So wrapping this up, what does it all mean for you? This research really confirms that this hybrid reinforcement approach, especially at that 4 weight percent of B4C, is a success. It maximized both strength and wear resistance, and it gives engineers a clear, cost-effective path for designing the next generation of high-performance parts.
That's it, exactly. But it does leave us with an important question to think about. If 4 weight percent of B4C was the best they tested, what are the theoretical and practical limits? At what point does pushing that ceramic content even further cause the benefits of hardness to be completely canceled out by that loss of ductility?
Something to mull over.